Let's discuss question number 39 from test 2. This is from supply pump, power plant, turbo machinery, saturated. Okay, so this is from thermodynamics, applied thermodynamics, but let's call it thermodynamics. Okay, so a supply pump, so you have a pump and it takes in saturated water at 0.01 MPa and boost its pressure to 10 MPa. So it's something like this. You can have like this. These are constant pressure lines. I have just drawn TS diagram. So pump takes in saturated liquid and pumps increases the pressure. So this is what is the process. Okay. Now as an adiabatic efficiency, okay, so this is how it does actually. The actual part is a straight line isentropic process, but actual will be this way. Okay, so now the reversible work that is done by the pump, that is if you don't have any losses or the process is completely isentropic, the work done by the pump is integral VdP. Now generally the specific, or it's very, liquids are incompressible, the density there is hardly any change, so specific volume can be taken out common. Specific volume is 1 by density is integral dP from P1 to P2. Okay, now saturated liquid density is almost 1000 always kg per meter cube. Ideal if is P2 minus P1, and so 1 by 1000 kg per meter cube. P2 is again your 10 MPa minus 0.01 MPa. MPa is 10 power 6. So this value comes out closer to 9.99 into 10 power 3, or you have 9990 kilojoules per kg. Okay, this is the minimum work required when there are no reversal. But if you have, because you have the adiabatic efficiency which is given as 0.9. Now this adiabatic efficiency is defined as the actually how much work you have done, that will be more than what is required. So reversible work is your minimum work. So a reversible pump which normally without any losses, an ideal pump, reversible pump will require less work. Okay, so this is the minimum work. So this minimum work by actual work is adiabatic efficiency. So this is whatever we have derived is the reversible work by actual work is equal to 0.9. So the actual work would be 9990 by 0.9. Let's use a calculator and see how much this value comes. So this is 11,100 kilojoules per, joules per. This was also joules because we have converted everything. So this is also joules per kg. This will be 9.99 kilojoules per kg. So I just written joules here. So joules per kg. This will be 11.1 kilojoules per kg. So the answer is A. Option is A. So this is again, you should basically know two things here, that reversal work, what is the expression, and also that specific volume is more or less constant in pumps. Liquids are generally incompressible, so you can take out common, and also the definition of this adiabatic efficiency. So the answer is A. Thank you.